So good morning, everyone, and thank you for the introduction. In this talk, I'm going to describe a model of what I think is could be, let's say, it's a toy model for streamers, and study their chemical impact in the protoplanetary disk to which they are accreted. Okay. Before that, I wanted to go to the basics, that is the star formation process. Okay. To highlight the process of accretion during all these stages. And it happens in all the stages and in all the scales. In particular, inside the protostellar core, we accrete the envelope, and we are left with typically a protoplanetary disk. And when we accrete all the gas or disperse the gas, we are left with the planetary system. Accretion is very important. When we classify these stages, we usually rely on the spectral energy distributions that somewhat reflect the balance between the mass of the central object and that of the envelope. But not only that, accretion is important in setting the mass that is available to form planets. It also induces instabilities. So these instabilities could, for example, trigger planet formation. An example of that is the Rossby wave instabilities. And finally, and I'm an astrochemist, so also accretion could induce local changes in the chemistry of the disk. In this example, there is an enhancement of deuteration where let's say the accretion lands on the disk. So I will just focus on accretion streamers. So accretion streamers here, you see an example of one of them, are observational features that are regarded as an ongoing accretion. So here in this example on the right, you have an streamer, this spiral arm, detected in HC3N 10^9 in parent 2 by Jaime. And yeah, you see here that it connects the envelope with the central object here, the protostar. Okay, so some properties of them are velocity coherent structures that connect the young stellar object with the envelope. And one of the main interest in these structures are that they may transport or channel chemically different gas from that is already present in the disk. Okay, in this context appears the concept of late accretion as the accretion of gas that is not initially bound to the star, but after some time passes and the disk has changed a bit of their physical properties, some gas that is regarded as fresh is accreted to the disk, and it may change their chemical abundance. Okay, so here I will talk about accretion, the appearance of streamers, how can we characterize late accretion, and if they can indeed bring chemically different gas to the disk, only from a modeling point of view with MHD simulations and chemical models. So I have no observations for you. Sorry for that. So let's start with the simulation, MHD simulation of a core collapse. Okay. This is known for some of you, but this is performed with Ramses MHD code. This is a core collapse. So we have a box with 5 solar masses of gas, magnetized gas with uniform density and temperature, and we let that evolve for 10 to the 5 years. We are using Ramses in the non-ideal MHD implementation, and we allow zinc particles to form. Zinc particles are just like the stars that they accrete, they bring luminosity, they eject material, and we also provide the simulation with tracer particles. Tracer particles are massless particles that follow the velocity field of the gas, but they do not interact with them, and they are useful to track the gas, to know, for example, the physical history of the gas that, for example, forms or belongs to the disk that will form eventually in the simulation. Okay, so we run the simulation, and we may characterize the disk. Okay, the recipe for the disk is a dense gas that is rotationally supported. Okay, this is the simple recipe for the disk, and if we follow that, we see this increasing trend in the disk radius here with time. And if you want some snapshots of the disk, this is how it looks like. So the increasing is not monotonically. Sometimes it is smaller, but in the general picture of the simulation, it gets bigger and bigger. We can also calculate the mass, okay, considering all the cells that satisfy this criteria. And the mass is around 0.02 solar masses and stays constant, relatively constant during the simulation. Okay. Now we can play with tracer particles. We can apply the same criteria to the tracer particles and call these tracer particles disk tracers. And here, for example, you see the cloud of tracer particles in the simulation, and we are interested in the ones that form the disk at the end of the simulation to check where they come from and what kind of properties do they have during their history. An example of their properties is, for example, the distance to the sink. So this is a bit involved to explain, but these are histograms at different time steps, okay, where I here showed you the amount of tracer particles at a given distance, okay? So this is where the disk tracers are taken, and we can trace them back in time to know where the gas of the disk comes from. And this is telling us that only the gas that is like 6,000 AU, yeah, 6,000 AU this gas is what ends up being forming the disk at the end of the simulation. Okay, so the gas that is far away from or further from the disk, from the sink, I mean, is not going to form the disk at this stage. Okay. But more important than the distance is probably the temperature. So here we are seeing a disk that is well around 250 K, and that gets, on average, colder by the end of the simulation. This is going to be important for the chemistry of the disk. Okay. Now, I told you about late accretion. It's gas that is not accreted at the beginning, but after a certain time where the physical properties of a disk have evolved and changed enough to be different from the envelope. So we may try to characterize this late accretion gas. And what I did first was to impose this condition here. So I only chose the tracer particles that are only infalling, okay, at all time steps. And I found, when I select the tracer particles that satisfy this criteria, I found these clouds of tracer particles. And by accident, I also selected the tracer particles that belong to the disk, which is here, okay, that are accreted only in the latest snapshot of the simulation. So this is coincidentally late accretion, okay. Here you see the pointer. Yeah. Here you may see also some channels of accretion that will be important later. But we can do the same analysis of the histogram with this cloud of tracer particles. So this is the distance again. But more importantly, I think, is the temperature, because what this is telling us is that all the tracer particles that are late accreted spend most of their lives at 10 Kelvin, but they are only heated at the end of the simulation. Okay, so this is again important for their chemical evolution, and we will see later what difference this may have in the chemical composition of the disk. Going back to the channels of accretion, here you see a zooming of the channels of accretion that appear when as it appears with the distribution of tracer particles. So these channels, I will go back here a minute. Whoop. Too fast. Yes. So these channels of accretion turns out to be these ones, okay? And these channels are actually the walls of some bubble-shaped structures. These bubble-shaped structures appear as a consequence of an instability, what we call the magnetic interchange instability, and is when you have excessive magnetic flux that you have to eject at some point. And this creates these channels of accretion where the late accretion can reach the disk, okay? So we have these channels of accretion, and we may ask ourselves if they look like the streamers we detect in young stellar objects. And to determine or to limit the extent of these channels of accretion, I chose a molecular transition that is often used to detect these streamers, DNC221. And in doing so, here you see this is a slice of the grid of the cells of the grid that satisfy this condition. And if we calculate the mass of all these set of grids of the cell, we obtain a mass of 0.03 solar masses and a size of 3,000 AU, 2,500. And we can also calculate the accretion rate, and it's around 1.7 solar masses per year. These are not crazy numbers, and if you check some streamers in the literature, they find similar numbers in their observations. So I think this could be a model for streamers. So we have our model for streamers, and we can check if they have a different chemical composition, if they bring different chemical composition to the disk. So for that, I use, again, tracer particles. Tracer particles are useful for to obtain the chemical abundances through time for the set of tracer particles that are late accreted. Here I use the chemical code Nautilus. So it is a complex chemical code, and we can model gas phase and ice phases, okay? And we have a lot of species, a lot of reactions. And as I said, we use tracer particles to find the chemical abundances of this accretion process. So we may start with the chemical composition of the disk, and we can start with carbon monoxide. So this is the gas phase, carbon monoxide, here on the left, and this is the ice phase on the right. So the first interesting thing I found is that there is a bimodality. So we have high CO, low CO gas phase abundances. And I wanted to understand why this is happening. Okay, you see this annular shape, yellow shape that corresponds to high, and you see the rest that is relatively low. So I decided to split these sets of tracer particles to see what's going on. And you see here the splitting. We have here the high CO abundances. You have here the low CO abundances. And here in this panel, we plot the average temperature history of these two sets. And we found that if the set of tracer particles with high CO gas abundances have a very different thermal history than the one with low CO gas phase abundances. So the one that has a high carbon monoxide abundance is what I consider early accretion and has this gray, not sure if the contrast is good in the screen, but this gray line here. And this could be regarded as early accretion as opposed to late accretion because the tracer particles that have low CO gas abundances, they are accreted late in the latest stages of the simulation, okay? The dynamic range in the CO gas phase abundance is not very impressive, but if we go to, for example, formaldehyde ice, the difference is much higher, okay? And early accretion, that means the gas that is, the chemical composition of the disk. The early accretion is much lower in the formaldehyde ice than in the late accretion that provides much higher formaldehyde ice abundances, and the same with with methanol, okay? And provided these are like the building blocks of chemical complexity, I think this is pretty important for the chemical composition of the disk and how we can understand the development of life in a planetary system. Okay, so these are my conclusions. So we have that non-ideal MSD simulations predict these filamentary structures that connect the envelope with the central object, and they appear as a consequence of magnetic instabilities. They act as channels of accretion that are similar to streamers that we observe in young stellar objects, and they may carry different gas with different thermal histories that is reflected in different chemical compositions that could, for example, in this case, that could reshape or replenish the snow lines of the disk, okay? So I haven't checked all the molecules, but for formaldehyde and methanol, there is a difference in the contribution of late accretion compared to the one that is already in the disk. And well, this is it. And before that, I want to make an announcement of a workshop. We are organizing a workshop in late November. So the dates are not fixed, but just have to have that in mind. We are trying to bring together simulations, observations of disks and planet formation to like bridge the gap between these two disciplines. Okay, so save the date and stay tuned for more updates on this. So I will leave you with the final slide. So thank you very much.
Thank you. No other question from.
Great talk. Thanks a lot. It's really nice to see that you coupled this chemical code with the Ramses. Mm-hmm. I guess you do that on the fly, right?
It's not on the fly. It's post-processing. I mean, we obtain the physical history of tracer particles, and then we provide the model with them. It's not on the fly. It's very difficult to do that. So it's the best we can do so far. Mm-hmm.
And so I'm wondering to what extent the dynamical timescales of these tracer particles mm-hmm. compared to the chemical timescales that Nautilus is, yes. Subject to. So can you tell us where, especially in your model, which timescales is dominant, and so where would you need this? Where would you need to implement Nautilus on the fly, to where the chemical timescales are typically shorter than the dynamical timescales? Would that be in the disk, in the inner region, in the outer envelope, or?
Well, that's okay. So our way of computing this is outside of Equilibrium. Okay, so I'm not really. I mean, I don't. I haven't developed the code Nautilus, so I'm not sure how the code. The inner workings of the code, but the thing is that we can provide the code with every time. With every snapshot, we have like a set of the sitting temperature that we can provide to the code. So the code computes in every time steps. So it's not. I'm not sure if that answers your question. The time scale is. This way, the time scale of the computation for the chemical code is equal to the time step of the simulation.
Yes, I have also a question about the modeling, but more on the chemical modeling. Could you show again your time dependence? Because it seems that you have very large instability. Yes, very large instabilities. You have several orders of magnitude difference.
Yeah, it's the log average of all the. I compute the log average of the abundances of all the tertiary particles in that. So that's why you see this kind of.
But these chemical instabilities, are they related to the physical instabilities, or it's only the result of
it's just an artifact of how I calculate the average temperature here, or the average abundance.